This conference will now be recorded.
Yeah. So, do you have you gone through basics of Redhawk, or what basically about PDN? May know on that. So, based on that, we can plan for the session.
Yeah, Raja, actually I'm into PD domain. So actually I'm getting opportunity to work for IRM. So that is the reason we have joined the course here, and we are looking
Okay.
forward for the course. And last couple of sessions, we have gone through like components of power, and it's the formula, respective formula, and how to calculate all those things, and how to reduce respectively. And apart from that, like we have briefly gone to like what is
Components of
dynamic
what did you say,
power,
Prasad? Power. Acha, okay.
components of power like switching, leakage, short circuit power, all those things in
Mm-hmm.
detail. And in the session 2, like we have gone through like briefly about the difference between dynamic static IR analysis, what is dynamic IR analysis, like how it is done, so, and the static analysis also. And also like here and there, like we have gone through some certain keywords like APL, FSDB, VCD, other things,
Mm-hmm.
but we want more understanding of those actually. Like it seems like we cannot read in some materials, so we need some more push for that actually.
Okay, okay.
Yeah.
Sure. Tarun, you're saying?
Hi. I've been in the industry for a long time. So in physical domain and across. So I thought.
Actually, somehow your voice is a bit low. Is it for everyone or only to me?
Yeah.
Uh, okay, I'll speak a little bit louder then. I think I've been in the kind of industry and chip design and physical design for a long time. So I know the kind of basics and all of that. So it's just kind of going through it in a more organized way. So I'm starting some airdrop work as well. So it will be useful. Yeah. So that's why.
Oh, okay. Thank you, Tarun.
Cheers.
Krishna?
Hello.
Yeah, Krishna.
Hi.
Yeah. So.
Actually, just now I joined. Sorry.
Yeah, sure, no problem. So basically, yeah, I wanted to know what is your understanding on VDN and what are your expectations?
Yeah, I have a basic idea of PD and PDN inputs. So I want to do a specialization in the power analysis. I have 2 years of experience.
In the PDN itself,
Not in PDN, PD.
PD.
Yeah.
Okay, good.
Yeah.
Okay.
So Raj, like basically, like almost all we are into PD, but we know like certain things for IRM, like DVD map, all those things. But like we want to understand more in a deeper perspective, concept oriented. Like so,
Mm-hmm.
that's where we are looking. So maybe you might have got some points now from us.
Yeah,
Uh,
that is true.
and
Mhm.
some of your background, Raj.
Yeah,
Is
so I am, I'm into PDN for, I have started my career with the PDN itself. I'm into
Okay,
PDN for my last 6 years.
okay, good to
Okay.
know.
Yeah, so yeah, Redhawk was the first tool we worked on. Then now the industry has it's moving on to Redhawk SC, right? So currently we
Mhm.
are on Redhawk SC. Yeah, but Redhawk is a tool to start to learn basics of PDN, and then it is almost similar, right?
Mhm.
Mhm.
Mm. So yeah, I have actually now don't have slides that were prepared by me. To go through it. So I was asked to use the slides that the institute has, but I see it was not covering the grid check portion. So are you comfortable with the grid check portion of it, where we actually doing it, what all we check? So I mean, even before all that, why do we first of all worry? Why have to be worry about the PDN, all that?
Uh, yeah,
Um,
Raj, like
okay, let me ask you. So I think uh, so if I may ask, so are you planning to do all the sessions from here on? Because I know there was a different trainer last week. So
Yeah,
if
correct. So that is not sure as of now, Tarun. So maybe at least this session, I don't have a particular agenda, and also I'm not very sure. I mean, you have just mentioned that you have gone through till some basics, right? But there is no structural presentation I have right now. Okay,
I mean, to be
because
honest,
what
I think I'm here to see kind of how it goes, but I don't think it will be good use of our time and your time if there is a no structure to it. We can keep jumping from one point to another and another. So
that's correct.
I think we need to have some contents and course material, if not course material, whatever, in the list of things we need to cover, and we need to do it one step at a time in a particular sequence. I don't think it will be a good use of time if we keep jumping from one place to another. So
Yeah,
I
yeah,
really.
that exactly. Yeah, even I feel that. So I was asked to basically conduct a quick Q&A session for this thing, but yeah, maybe we can do that. But otherwise, as a if it has to helpful for you, it should be a structural training.
Mhm,
So as you guys are expecting, right? So I think we should
mhm.
start. First of all, the material should be there. We should
Yeah.
work on the material part and the presentations.
Mhm.
So that's looks like we don't have it right now.
So is that something you're going to talk to Srinivas? We
Yeah, yeah.
should
So
do that.
I'll be talking to Srinivas on that part, but maybe this session, today's session, we can use it for any Q&A based. I mean, on the topics that you have already gone through, right? You can we can discuss if you have any questions.
Also, if you are comfortable, it would be good if you show us some kind of tool in this session. So, the basic things on the tool.
Yeah, yeah, correct, Shailaja. Sure. So for that, we need to set up the tool in the environment they have. Even on that, I have to talk to Srinivas and understand what all we have to set up. And once it is set up, even we can set up some labs for you to run all different checks that we have, and also we can go through individually to help you out what we generally check in each of those checks, and how do you debug all that. We can help out.
Okay.
Yeah, so yeah, right now we can go through if you have any questions based on your existing learning.
okay, yeah, understood, Raj. Yeah, like we are aligned with you too, since we do not have any structural VBTR presentation material. So what we can do is like whatever we have, the queries from earlier sessions or from earlier videos, probably we'll bring that. If not into deeper jump, so let's at least give us some overview of that, and probably in regular courses, like I mean regular sessions, you could. I mean, we'll definitely bring that by marking that. Probably later, like you can give us a more detailed explanation there. So,
Yeah,
being that
sure,
said,
sure.
I would like to start. Like,
So
if
even
nobody
so
have any.
basically, I was given some videos. Basically, I was pointed to some videos from the institute. So I don't see grid check portion covered. So,
Okay.
but that's the important items when we start with the design, right? So, are you guys comfortable with that? or was it covered already, or have you
Not
directly started with DVD and static portion?
No, it is not
directly
covered.
we have not covered actually. Probably if you can present it in a paint or something now, that is also okay.
Oh,
Yeah,
okay,
that will.
okay.
Next motion conduct. Yeah. If
Yeah,
not,
sure.
like we will go with some whatever we have some questions. If everybody are okay with that.
Yeah, sure. So basically, maybe I'll spend some time on the grid check portion, okay, and
Mhm.
then we can move on to the questions.
Sure, sure, Raja. Yeah, at least like you can start with a overview of the Red Dog, why it is needed, what is the scope, and what is the importance of IREM team in a PNR. So probably we can go through all those things and like
Yeah,
what needs to be
sure.
checked, all those things. So probably you can give it. Yeah, thanks.
Okay. Yeah, yeah, sure. So just trying to, yeah, I'm sharing my screen. Can you see my screen?
Yeah, yes.
Okay, how do I minimize this? Yeah, okay. Okay, so yeah, so first of all, why do we actually need to worry about IR drop analysis, right? So if you see, when we are implementing the design in the PD cycle, right, we close static timing analysis. We close, timing, assuming that you would get uh, a particular voltage at the transistor pin, right? But in reality, you have some, I mean, the network, right? So it starts from your, you know, PMIC is your actual source of the power. So you have ideal voltage supply. For example, if you assume, 1 volt is at the output pin of the PMIC, and you have transistor somewhere on the die. You have transistor pin here, right? So in between you have package layers, and then it is all your die, right? In the die you have all uh, metal layers, and then vias through it, right? It is all R and L network from PMIC to the pin of the transistor, right? Sorry for the bad drawing, but so so
No problem.
here when you are when you are closing uh, you know timing path in STA, you would assume that, for example, this is your timing path, right? This is your end point and start point, right? So you would assume that each of these instance will get a voltage of, for example, um,
Oh,
zero point
sorry,
0.9 volts.
would you mention again what is PMIC?
This is PMIC. PMIC is another, yeah. This
Power
is like another chip, okay?
which is
Another
power
chip that
management.
would go onto the package, and
Mhm.
this would generate the supply that is needed for the die.
Okay, yeah,
Okay, so
sure.
on your die you might need all different kinds of supplies, right? Maybe you will have some portion of CPU, graphics, or multimedia, all different subsystems you will have,
Hmm.
and each of might work in different different states, and
Okay.
you might want to, let's say, have CPU in a high frequency mode, and at the same time, for a case, you might want to use graphics in low frequency. So all that is controlled by the voltage that we give to each of those cores, right? So that's why we would generally have separate voltage rails for each of these modules. So all these voltage rails are generated by a separate chip called PIMIC.
Okay, sure.
Okay, so this is so internally. So I mean, we'll have a one supply that is something like a battery, and with that supply internally, this PIMIC also has a complex design inside, and basically it generates all different supplies that are needed for your die. And from this PIMIC pin to your transistor pin, if you look at the connectivity, so you will have on the die there is a package, right? Package. So there is, like, let's say, package that you have, and here you will have the package balls connecting to PCB routing. So on the PCB, if you look at the PCB, right? So something like, let's say, if this is PCB, you will have your main, for example, your main die here, and PIMIC will be another separate chip on the same PCB. So from this PIMIC to this die, then you will be connecting on the PCB through the routes. Okay. So, and if you take this die, uh, basically this die will be connected to the PCB through balls. So these are called balls. Okay, so each ball, then inside the package, each ball will supply multiple, we'll call them bumps. Okay, so these bumps then connect to the die. So die is where the actual silicon starts, right? So this is your die. Then these are your, let's say, bumps, right? So now these bumps are connecting the package to the topmost layer of your die, right?
Okay.
For example, if we call it, if we assume there are 13 layers in this die, this is your topmost layer, which is M13. And then from M13 to, if you assume the lowest metal as M1, right, you will have a mesh structure connecting this M13 to M1. So something like, for example, if you have M13 vertically, right, you have bumps like this, bumps, and then your next layer M12 will be horizontal, right? And then so that would be connected through the vias. Likewise, you'll have vertical and horizontal layers creating a mesh and helping the current to bring it to the transistor pin. So this is the lowest metal layer where you have the transistor VDD pin of the transistor, right? And on the other side, this is VSS. Even if you look at the VSS, the similar, again, the structure is there for even VSS also. So your overall drop now, for example, if you're giving 1 volt here, right? 1 volt
Okay.
here, right? You might have, for example, assume some 50 millivolts of drop you have in VDD, and here it reaches 1 volt minus 50, right? So 1.950 millivolts, sorry, 0.950 millivolts. And then on the VSS side also, if you, for example, the same, so VSS is no different, it is also same structure. The VSS pin of PIMIC again connects to the VSS grid, right? Similar structure will be there. So you might see even similar drop over there also. So if you are giving 0 here, the drop that you would see, right, would be 50 millivolts, right? So the differential voltage is what that is finally applied to the transistor, right? This transistor. So you have 950 here and 50 here. Finally, you're seeing only 0.9 volts here. But this is the ideal scenario, right? Uh, so when I say ideal, okay, I mean, this may not be same for all the transistors, right? So this particular transistor is, seeing zero point 0.9 volts, but maybe, I mean, there could be several reasons. Maybe the current demand of this particular transistor is high, and maybe the grid around this transistor is weaker. Because of all these reasons, you might get only maybe 0.85 volts for the next transistor, right? And maybe the other guy might see a better scenario around it. Maybe even the current sharing is not much around this transistor. It might see even better than what you assume. That is maybe 0.92 volts you're getting here, right? So, so all different kinds of, in reality, all, though you assume zero point 0.9 volts and close your timing in your ST environment, in reality you might get different voltage at each of these transistor in the timing path. One is 0.95, zero point 0.9, or it could be 0.89, all the different voltages, right? So if with this voltage, now when you redo your timing, right? So whichever, for example, if you are seeing zero point 0.9 volts, then this would give same delay as what you have expected and closed in your timing. But this particular transistor will give uh, more drop if, more delay if the voltage is not zero point 0.9. If it is in case 0.88 is what you're really getting here, right? So then this will give more drop, more delay than what you have actually assumed when you have closed your timing. So accordingly, overall your final timing will change, right? So by PDN analysis, what we are trying to do is, so there are actually, if you take practically, right, there are different methodologies followed by different, I mean, in terms of what should be the drop from, let's say, PMIC to the transistor pin, right? So it could vary from, one design to other design, or one company to other company. They might have some internal methodology, and accordingly they can follow. But assume, let's say, if you're saying, let's say 20% drop is what I can. So this number, that is, this comes from their previous designs and the type of their designs, and also even in within a company, based on a design type, there could be a different application. There could be auto application, there could be mobile application, there could be server application. So based on that also, it can vary based on their silicon learnings. They will refine these numbers, and accordingly they will set, based on their methodology discussion, they will set these numbers. So for example, if you set it up to 20%, so what does that mean is, you're trying to meet a total drop of VDD plus VSS drop of 20%, right? 20% overall. It doesn't mean that you're even if it is, see, when you say 20%, many of them could be below 20%. If you actually look at the variation, right, it could be something like a bell curve. So you'll see 20% will be somewhere over here, but the average number will be less than even 10%, right? So with that, even if some instance is a bit, the drop on some instances is a bit higher, you will overall be safer in terms of meeting the timing on that path, right? So this is what our target is. Basically, we are trying to uh, in terms of the IR drop, we are trying to be within a defined limit, in order not to be off from the STA closure that we have done, right? Assuming some ideal voltage on the transistor. Is that clear?
Yeah. Yeah, Raja. So,
Yeah, yeah, that's
like
okay.
you
Yeah.
mentioned, we have both VDD and VSS pins, right? So, like we'll have a connection from RDL. I mean, let's say package only, or let's
Exactly.
say
So,
RDL.
okay, so
So,
correct. So let me, so see, it is like on the same, see, this is, for example, the transistor, if you say, right, you have
yeah.
VDD pin, and this is, okay, if you take the primary rail itself, right, this is VSS rail, and this is VDD rail, right? And for example, this take it as M1, mm, M1 rail, and you have then M2 rail, right? So this M2 rail is for VDD, this M2
Okay.
rail is for VSS. So you will have a via over
Okay.
here, and you will have a via over here, right? Connecting to M2.
Yes.
So likewise,
Yeah.
you have mesh for VDD going up to M that we have seen, right? M13, right?
Okay. Topmost layer.
Similar
Okay.
mesh for VSS going up to M13, right?
Okay.
So it would be, I mean, almost similar net, because the current that flows from VDD, obviously it should have a return path. It has to go through VSS. So,
Yeah, that
you
was the
know,
question I had in my mind. Like, because you said you some amount of voltage is getting dropped from the VSS layers, right?
yeah, yeah, yeah. So it is in fact,
So,
it would be almost similar. Whatever you see, I mean, if the structure is same, right? The
uh
density of the mesh is same. Whatever you would see in VDD, similar drop you will see in VSS also. That's why when I say, when you apply, for example, 1 volt, and 50 millivolts is here, and almost 50 millivolts in VSS as well. Okay. And then effectively, if you look at the instance, right, effectively you have 100 millivolts of drop, right? So though you are applying 1 volt, I mean, though the PMIC is supplying 1 volt, you are getting only zero point 0.9 volt applied across the instance.
okay, you mean like we are applying 1 volt. Let's say we are applying 1 volt to that instance, and in the VDD path, it is I mean 50 millivolt of drop is occurring,
Hmm.
and the same current while it is going out from that VSS path. So it is I mean we also encountered 50 millivolt of
50
drop.
millivolts of drop,
So
correct.
so overall, like 50 plus 50, like around 100
100
millivolt of
millivolts.
we are losing out of 1 milli, and zero point 0.9 volt it is reaching the instance, right?
Instance, correct. So
Okay.
only
Okay.
see, it actually depends on what are you applying between VDD, its VDD and VSSP, right?
Okay.
So since there is a mesh here, it is like, if you check in reverse way, right? So it is like you're applying a 0 volts on VSS, right? But because
Okay.
of this resistance, you would see a drop here. It's like there is a VDD VSS bounce, right? 50 millivolts of VSS bonds, and here, so I mean, for example, if you look at a resistive network, right? This is your instance. Um, this is like if you totally replace the whole structure of this mesh with a resistor, right? You have a resistor in the VDD arc, and you have a resistor in the VSS arc, right?
Yes.
And this is your PMIC, if you want to like simplify it. This is 1 volt, right? And the current is passing through this mesh, and through the instance and coming out. In fact, it is all connected on the ground, right? Yeah. So you have, because of this current multiplied by the resistance, you have some drop, right? 50 millivolts. So the same current is now going through the VSS also, and since we are saying the mesh structure is same, so that even the drop will be same, right? This is 50 millivolts, right? So if this is zero, right, and if you add 50 millivolts here, that means if you look at this node, that is actually 50 millivolts of bounce, no? And if this is 1 volt, and if you drop 50 millivolts, and if you look at the node here, that would be 0.95 volts, right? So effectively, if you look at the drop or the voltage across the instance, it is only 0.95 minus 50, it is only 0.9 volts.
Yeah, understood. Like you brought up some word bounce. Is that a ground bounce? What we
Ground.
heard while reading that? Can you elaborate that? Like why it is called like ground bounce?
Oh, why it is called? Yeah, yeah. So basically, I mean, see, it is like ideally we want it to be. I mean, when you have a transistor, right? Ideally, this VSS pin voltage we want it to be zero,
Yeah. Yes.
right? And
Yes.
ideally, we want the VDD pin to be the PMIC voltage, right? But
Yes.
because of this resistance, right, the resistance between this VSS pin of the instance and the PMIC, the voltage you see at the pin actual pin of the instance is not zero, but it is the drop basically. As I said, as I just explained it, if this is zero and if there is a 50 millivolts of drop in this resistance, then it has to be 50 millivolts here, right? The node voltage at the instance pin should be 50 millivolts. So ideally we want zero, but it is showing 50 millivolts. That's why we say it bounce. See, even if you look at in a dynamic scenario, so this is like a static analysis. So even if you look at a dynamic scenario, right? If you look at the waveform, VDD waveform at the pin and VSS waveform at the pin, it will be something like this. VDD will dip whenever the instance switches, and VSS will normally be zero, and whenever it switches, there will be a bounce, right? Then the effective voltage across the instance is the difference between this and this, right? So that means even a drop is bad to the instance, right? And even a bounce is also, it is something unwanted for us. Both of them will act on the instance, and finally the effective voltage that is applied across the instance is reduced.
Okay.
So yeah, since it is, I mean, more than zero, there is a terminology as bonds. We call it as a bonds. So on the VDD side, we say drop, and on the VSS side, we say it as bonds.
Oh, so will that so the VSS path current will be, I mean, negative or what? The drop is negative or like positive only?
No, this is here it is like a 50 millivolts positive drop. I mean, if
Okay.
you look at the voltage, right? Okay,
Yeah, yeah,
let's
yes.
talk in terms of voltage. So this is a 50 millivolts positive voltage.
Okay.
Okay, and this node has zero voltage, and this node has 50 millivolts of voltage. Then through that means through this resistance there is a drop of 50 millivolts. So your current flow is always even in the VSS path also, it is from the VSS pin to the PMIC, the 0 volts node of the PMIC,
Okay.
as I've explained here, right? So basically, this current, um, this is like your positive flow, right? Positive charge flow. It it is in this direction. Even in the VSS resistor, also it is in the same direction. It is going inside and going through the instance and reaching the ground, right? So since this node is tied to ground, when this much current is going through this resistance, that is creating a positive node voltage on the instance pin. Did you get it? So basically, this
Okay.
current is something that is pulled by the instance, right? Once it is pulled, then it has to go through the ground, right? So once it goes to this resistor, and the one side of the resistor is connected to ground, obviously if this amount of current is going through this particular resistor, and one side of it is tied to ground, the other side has to be over by the same amount of drop, right? So that's why we are saying this would be at 50 millivolts of drop.
Okay. 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 Got it.
Got it, right?
Yeah. Yeah.
Okay, so
So you're like you mean to say we uh, like if there is a more drop in the VSS also we should reduce it so that
yeah. So see, VSS and VDD are equally important.
okay. Okay.
And in fact, if there are if it is a multi-domain design, right? Your
Hmm.
when I say multi-domain, so basically, let's say if you look at a single subsystem, you might have, for example, memories, right? Memories, and this is a core region, right? So so in general, I mean, this is a design style again. It might differ from design to design, but in general, these memories we will operate with a supply, because I mean separate supply, right? It will have its own mesh, and uh, from the PIMIC there will be a separate. For example, you call it MX, right? So there is a separate supply connecting to these memories, and even the core region, there will be a separate supply, okay, connecting to this core region. So this I'm calling it as multi-domain design. So here in this case, the current required for memories and the core is coming from two different mesh structures, right? But the return current has to go through ground only.
Okay.
You got my point. So here you have for a mix, and for example, you assume this is supply A, and this is supply MX. Okay, for memory, you assume it is as MX. So you will have then you will have different mesh structure for memories,
Yes. Yes. We have
starting
seen.
from the
Yes.
PIMIC MX pin to the memory pins, and then different mesh structure for the core region, starting from PIMIC to the standard cells of the core, right? But
Okay.
so that means the actual current um, that is needed by memories and the core region is coming through different layers, right? They are not shared, so the drop will be relatively smaller if you are actually let's say if smaller than the case where if you are connecting these memories to the core itself, right? So then even for the memory current even the memory current has to come from the same a the stripes that you have given for A, right? So, but the return current, obviously, even for the memory or the core, has to go through the ground itself. So you'll have a common ground across memory and core, right? Common mesh across memory and core, and then it will connect to the VSS of the PIMIC. So what I
I
am
mean,
trying to say here is,
I,
here
I
in
mean,
this case, yeah,
okay, is it fair to say generally it is a one VSS and it could be multiple VDDs for different subsystems, but if required, if the drop is too much in VSS, we kind of technically could have a separate VSS as well because there are separate VSS for analog. Is it?
yeah, see, for analog, I think we would do, but in the core region, for all digital in general, you will have only single VSS across the
Right.
chip.
In
right?
general, we have, but if required, we could always kind of have a separated VSS as well. But generally, yeah, you're right. So it is generally one VSS.
No, but what are we gaining, by having different VSS in the core itself, right? So because see, if we have since the written path is common, see here
Hmm.
the basic idea of having multiple domain is to control them separately, right? Maybe
Hmm.
in a scenario, I may not want to turn on this core region. Then I can just switch off this domain, and
Hmm.
I can save power on this domain, but I can still have these memories on. Maybe these are giving some data to a different block, right? These are going as input to a different block, so I can still have them turned on so that this block works. But I can
Hmm.
still using this supply, I can turn off this core region, right? And finally I'll be saving power, right? So that is the
Hmm.
reason why we, in general, will have different supplies connecting to different portions of the core. But the VSS can be common, and when you have a VSS separate, so you can have it, but I don't think there is an advantage, because when you have them common, that there is an advantage. So whenever, for example, you're turning this off, and you're trying to use only memories, then your whole mesh that is available is supporting these memories. So your
Right.
your drop is improving on the VSS side, right? So
Right.
when you
Yeah.
have a shared mesh, it would help. It would help all of them, because the peak activity may not occur at the same time in the different portions of the chip, right? So
Hmm.
whenever a portion needs very high current, then your overall structure is going to help that guy, if it is shared.
Hmm.
But
Okay.
if
Sure.
you have it in limited to that particular portion, uh, the other one is not going to help you, even if it is not on, right?
Hmm. Okay. Sure.
Yeah, so that's the reason why at least we try to make all the digital portion common, and we make VSS continuity across the chip as far as possible.
Hmm.
Okay. Yeah, there was some other question. Any other questions on this?
Yeah, I understood, Raj, actually. So that is why like the grid should be evenly distributed both in terms of VDD rails and VSS. So
VSS rails.
as we have both importance of both. Um,
Yeah,
yeah,
exactly.
got it.
So the actually in Redhawk, right, the first thing, I mean, we have, as you have heard, multiple checks, but the most frequently used is this guy. So that's why I've been asking about this. Um, and we would actually start doing this from the early DB itself, grid check. Okay,
Mm.
and
Mhm.
then you have static, dynamic, all that, right?
Okay.
So let's spend some time on this grid check. Basically, what do we do in grid check, right?
Okay.
So, and at what stages we would do. So, as I said, grid check is something that we actually do at each stage, right? So this is a simple check that can catch any weakness in the grid, right? So
Mm.
so basically, when you, as we have seen, so this is basically for the die level analysis, right? From M13, the die, if you take, for example, M13 to M1, you have, VSS and VDD mesh you have, right? And so what we are trying to do is, in this grid check analysis, we are trying to check what is the resistance of each instance in the design, right? So we are trying to extract a parameter that is resistance, and more specifically, it is shortest path resistance. Okay, do you guys know? You might have heard about it already, but can one of you tell me what is shortest path resistance? Your understanding of shortest path resistance?
I think it is a least resistive path uh, from the, like if you take from a bump, any, I mean any bump to the power pin of the instance, least resistive path we can say,
Yeah,
from
that is correct.
bump
That is
to
exactly
pin
correct.
of
So
power.
okay, so basically, okay, so think of this design, right? You have started with floor plan, right? And then there is, you will draw the PG grid, right? Once, for example, you have memories over here, and there are some custom IPs over here, and rest of it is core region, right? And accordingly, you will draw, whatever the type of grid that you would need for memories, you would draw, and the IP connections you would make, and then even the core region, since you're planning to add standard cells over here. Accordingly, you would create some mesh structure for both VSS and VDD. So once this is created, then this DB. So now let's say we are calling this as flow plan DB, right? So just you have placed the macros and IPs, and then the rest of the core regions you have standard cell rows, and flow plan DB is ready. Now you will take this flow plan DB through your PNR cycle, right? So in the place you will add standard cells, and then in the PNR cycle you will have say CTS, uh, and then you will start with timing issues, all that multiple iterations it goes through. So during this journey, and you want to make sure that the grid that you have created in your flow plan, right, that this doesn't get disturbed. So this can happen basically, and if you, while you're trying to run something, maybe some PG may get, some vias may get removed, some PG may get, I mean, it can be because of the blockages, or even it could be sometimes intentional chop also. When you're trying to fix a congestion issue, you might want to remove some PG, right, in order to create some layers for routing. So all that can happen, but in even while doing that, we don't want to mess up with the overall resistance of the instance. So finally, the quality that we have created in the floor plan, we want to make sure it stays till we tape out this design, right? So that is the reason why we keep on doing this grid check throughout its cycle. So starting from the floor plan, as soon as you have this mesh created in the design, right? We would start doing that, and then once the floor plan is done, and when you start placement, so in the floor plan there will be only fillers, right? So you'll have only in the core regions you will have only physical instances just to create those rows, and make sure that PV is clean. Then once it goes to the place, then you will place the actual standard cells, and once after placing the standard cells, again you would validate whether with respect to grid resistance I am fine or not. And through the even the PNR cycle, through the ECOs, till your final tape out happens, you will keep on doing this. So I feel, so this is one of so why I think this is simpler than the remaining ones, at least to check the quality of the grid, right? Remaining guys would need some additional inputs, and also even the runtimes will be higher, but at least to see to the first level whether the grid quality has degraded or not. So this is widely used check at each stage of the PD cycle, starting from the flow plan till the tape out, right? So what do we exactly do as part of grid check?
Uh,
So you
Before
have, as I
going to
said,
that, like,
yeah,
so one
hello,
query. So to,
yeah,
yeah, Raj. Before that, I have one query. So in order to check this grid check, so all the PG should be enabled in the earlier stage itself, like before floor plan, right? Like an entire grid.
That is correct. PG should be there first. I mean, so in the floor, say, okay, that is floor plan stage itself. But even before the PG, you would first of all place the macros, memories, or if there are any IPs, those has to be
Yeah,
placed
that
first.
will place, but usually stand like let's say once we do the floor plan, the standard cells won't be placed, right? So in that case, how it will try to calculate the, what is that you said, resistance path, right?
Resistance, right? Yeah. So
mm,
in place of
how it
standard
will,
cells, we will have the
yeah,
fillers. In see,
okay,
for example, if you assume, so if this is your core area, right? So you will have the standard cell rows, right?
uh-huh.
Right. Then in floor plan stage, you will have pillars in place of standard cells. You don't really add the actual standard cells of the design, but you have to add the fillers. Even for PV cleanup, all this needs to be added with fillers, physical cells. So then once it
Okay,
goes
but
to the play stage, these fillers will be removed. Then actual your standard cell placement happens over there.
okay,
Where are
because
we
we
doing this?
don't
Are we
like,
doing it in ICC to Innovos, or are we doing it somehow in Redhawk? Where are we doing this filler placement?
No, see, even in Innovus we can do this filler placement.
Okay, I mean there might be, I mean, a tool. What sometimes tool limits what you can do is, because if there are standard cells, if there is a design loaded in Innovus and the design has the standard cells in it, so you either place standard cells, or I'm not sure you can not place standard cells and do the fillers. I'm not sure, is it?
No, that can be done. See, here the standard cells won't be loaded here. The only the rows will be created, right?
Mhm.
Your standard cell placement doesn't happen here. The rows will be created, and on the rows you can add fillers.
You can add fillers without placing the standard cells. Uh,
Standard cells, exactly.
will tool not give you error?
No, no, no.
Okay, all right.
So only so in the play stage, right? There, then you will again take the non-filler inserted DB and then start placing your standard cells.
Okay, I'll take your word for it, and we'll, when we come to labs, we'll see. Yeah.
Yeah, yeah, sure.
So Raj, so are you telling that when PD is doing their floor plan for EMIR analysis, you would actually latch onto the floor plan DP without placement, do filler cell placement, and then do an analysis, or
No, no, not specifically for EMIR analysis. It is basically for the floor plan when you are starting with the floor plan, right? It is not only specific to the EMIR analysis. So obviously EMIR analysis, if you talk about IR analysis or EM analysis, that should be done with the standard cell placement itself, right? Since we don't have a standard cells placed here, since this is a early DB where you have just placed, where you have just freezed the macro placement and IP placements, and then now you know where your core area is, right? Now after doing this, you want to check whether if there is any problem with my grid or not, right? If there are any there are some items to check whether all the this is a standard cell location, for example, right? So if I really add a standard cell here, will it be connected to my grid or not? That is something I have to check, right? So
okay?
that is something would be done in floor plan itself as part of grid check. We are calling it as grid check, but this EMIR analysis will come a bit later when actual standard cells are placed.
So for this grid check, the fillers have to be there. Are these fillers needed, or we can do a check without other fillers?
No, you at least in Redhawk you cannot do without fillers because the resistance check actually checked on an instance, right? So it cannot, if you simply have a standard cell row, you cannot simply check what would be my resistance at this point. This is not easy to check, unless, I mean, there are some ways, but that you can do effective resistance calculation and all. That takes a lot of time, and it won't give you a clear idea. So that would be a coordinate based check, but that won't give a clear idea. So generally, the widely used approach is they add the fillers. When
Okay.
you don't have a logical standard cells added, we add the fillers. Now you would treat these fillers as your actual instance, and you would evaluate whether what is the resistance to this particular filler, whether it is properly connecting to my grid or not, and what is the resistance to each of my fillers that I am adding here. So that would, that is in turn telling me whether this location is okay to add standard cell or not. If the resistance of the filler in this location is okay, then I know that okay, I can even add standard cell, it would be okay.
So this the check is a resistance to the PG pin of the filler. Is that
Exactly. Power and ground pin of the filler.
okay? So adding fillers is a requirement for this
Yeah,
particular analysis.
that is must in the floor plan DB.
Okay, thanks.
You can see if you have void spaces, right, then you're not really evaluating that particular cell, I mean the standard cell location in terms of resistance. So if you are trying to add a standard cell in play stage, right, then you would catch if there is any issue in that location, then you will catch only in play stage. And if there is a real issue, that would be late, right? Then you might need to go to place back to fix that issue, sorry, floor plan back to fix that issue, right? So just to avoid that delay, right? I mean, we don't want to go through the iterations, right? So once we are done with floor plan, we want to make sure it is proper, and then we want to go to the next stage, right? So here, that's why we add the fillers, and we evaluate the resistance on these fillers and to see if there are any issues.
Correct. Now, right from the first stage of placement to the way till the ECO, the utilization is going to go up, right? So at different stages, we have different vacant spaces. So do you add fillers at all these stages or only at the floor plan stage?
Yeah, see, that's the recommendation. Basically, we would, whenever it goes to Redhawk analysis, uh, the void spaces needs to be filled. So
Okay.
that's when we know that that we are going to evaluate that void area, and in case if there are any more ECO cells come and sit in that void area, right, in the future stages, that's going to the area is going to support. Otherwise, then that would be a missing spot for you. Only when it is added, you're going to catch it, and it will be late. By then, it would be late, and you have to churn out extra iteration to fix that.
Correct. The problem is sometimes the initial utilization is very low, but way down, a lot of cells will get added, and it will be a huge load for the IR network, right? The power network.
That is
So
correct.
this will be taken care of, if you do add fillers. Is that correct?
That is correct. Yeah, filler. That's why we have to add fillers and evaluate all the regions.
For a design, is there any sign-off number for the short response path? Technology, with respect to technology, there should be a sign-off
Okay.
number.
Yeah. So that totally depends on the technology and even the PG structure. Okay, I'll come to that. So yeah, there is no single number as such. Okay. For example, okay, if you go into the details, right? As I said, you have this mesh structure, like M13 is there, and maybe I would for example, this is a HM that works on low frequency, and and I might not need a dense PG here, right? Based on the power density, right? I expect on this HM. Then what I would do is I don't draw a density PG structure here. I might have a relaxed pitch. For example, M13 is here, and then in general top layers pitch will not change much, but when I go to the lower layers, that's where it can help my routing. So if it is not critical for IR, I might want to increase the pitch of my PG in the lower layers, right? Like this, for example. This, consider this as your lower layer, right? Maybe M2, and this is your standard cell, maybe M1, right? So generally, how do we do this grid SPR check? Is it we would add a virtual PLOC. PLOC is pad location. Since we are, so this analysis is done at only die level, right? We are not including the package, and we're not including, PMIC or pad, sorry, PCB inductance and all, right? We are at first level, our HM floor plan is ready, and at that level, we are trying to see whether our grid is fine or not. So then we would add. What we are trying to analyze is from the top layer that we have in the HM to the lowest metal pin, whether the grid structure is proper or not, right? So for that, what we do is we add a pad, virtual pad on the top layer of your HM. So basically, this is a requirement by the tool, right? To trace, to create any connectivity, it needs a PLOC. So in Redhawk terms, they call it PLOC, pad location, right? So there are tool commands to add this virtual pads. Basically, you can mention, okay, at what coordinate you want to add, or you can even script it saying, okay, on M13, I want to add pads this pitch, right? And something like that. You can even script it and give it to the tool. Accordingly, it will add these pads on the topmost metal layer. So when you add this, and then when you do the grid check, so what it does is it tries to calculate the shortest path resistance from these pads to the each of the instance pins, VDD and VSS. So if this is VDD M13, you also have VSS M13 and VSS pads, right? So there will be resistance trace from VDD PLOC to VDD pin of the instance, and also VSS PLOC to VSS pin of the instance, right? So as I said, so this would be a shortest path resistance. So shortest path resistance is basically, this is a mesh structure, right? And if you look at the actual scenario, even there is a pad here, there is a pad here. So there will be some current contribution from this pad also. There will be some current contribution from this pad also. And this is, since this is a mesh, there can be numerous amount of paths, current flowing paths possible for this instance. So the current can come from here, and when it goes to M2, it can come from here, like this, even here. So numerous combinations are possible, and in reality, all these paths will support the current of this instance, right? Uh, but when it reports a resistance, it actually reports the least. So basically, for all these paths, for example, if you have to find out the resistance, so you have all different resistances um, to this instances from PLOC. So it is like you have an instance, you have multiple PLOCs, and you have one resistor like this, one resistor like this. It's not so simple. Even you have multiple nodes in middle, but as a simplified structure, right? Something like this you
Whether
have.
it is a like effective resistance, like
No, this is not effective resistance. uh, uh, yeah, I'll come to effective resistance a bit later. So
okay.
basically, uh, just assume, so you have all different paths possible to this instance from each of these plogs. Even from a same plog, you can have a different path um, uh, coming through the when it comes to the lower layers, right? It can have a different path. It can choose a adjacent metal to reach this instance. So all these are all the available paths. But if you look at the resistance, the path that gives the least resistance, right? In general, that will be very close to this instance. For example, this M2. If it has to reach to this M2, obviously it is going to add this extra piece of wire on M1, right? And lower layers will give a lot of resistance. So in general, if you look at the SPR, right, it will be the closest metal that is available near the instance. So it might be something like this M2 it will take, and then the next M3, nearest M3, nearest M4, something like that, it will reach to the nearest pillar. So this is called the shortest path resistance. Okay, so so basically it is the least resistance among all the available paths for that instance. You have numerous number of paths, right? And what is the you have all different resistances of these paths, and what is the least resistance among all these paths, and this path is for example, if this is the least resistance, this path is called as the shortest path resistance of that instance. So when you are when we are doing a grid check, and the tool that is going to report the resistance is nothing but this shortest path resistance. Okay, that is because if you have to actually find out the effective resistance, you have to solve this whole grid structure and see what is the total effective resistance from the P log to the pin. So this is something that takes a lot of time in Redhawk, and also even your uh, uh, even the machine configuration also. In fact, even if you want to do Redhawk was not really capable of doing effective resistance calculation for all the instances is in the design. Maybe hardly you can do uh, for a selective number of instances to really evaluate if that is a concern or not. Maybe if there are some outliers in based on SPR, and if you want to evaluate if they are really a concern, you can check specifically for those instances. You can check effective resistance and see if they are really a problem or not. So likewise, we generally use effective resistance calculation selectively for some instances, but if you have to do for whole design, this is the only thing that is widely used, SPR calculation, um, that is being done as part of grid check. So in grid check, basically when we are finding out the resistance, as I said, it is the SPR of each of the instances in the design. And that too, when it reports SPR, it can report for VSS and VDD separately, VSS arc and VDD arc separately. And so accordingly, now, so you got the resistance of each of these instances in the design, and obviously it cannot be same, right? So because see, one instance, if it is sitting in the middle, it is a bit far from M2, right? And one instance if sits just below this M2, then the amount of M1 it has to travel to reach the instance is pretty less here. And if you see, the lower layers will offer huge resistance, and this itself will give a difference of 30 to 40 ohms between this instance and this instance. So accordingly, when you are doing the grid check calculation, right, you will profile your resistance histogram. Basically, once you are sure that okay, my grid is proper for this particular grid structure, how is my resistance profile? Maybe, for example, it is starting with the lowest is 1000 ohms, and maybe highest is going up to 1200 ohms. Then then you would review these outliers, and you would see that is there a real problem with this 1200 ohms, right? So then you might see that okay, the instances are actually in the middle and they are traveling longer on the lower layers. That is why it is higher than the actual average of my chip. And also in some cases, basically, if the instances are sitting in the edges, right, edges of the core, then obviously it has to, for example, if your mesh is like this, right, it goes like this, and this is if this is your boundary, the instances in the edge, you can't get a stripe on the left side because this is your boundary. So in general, we would see higher resistance on the edges because of that reason. So, but you cannot really do anything. This is how, I mean, this is expected, right? You don't get multiple paths over here. So then you would realize that okay, 1200 is okay. These are some cases where either the instances are in the middle of the stripes or the edges. Then you would set that okay, 1200 is my limit. So if this, for this particular grid structure, right? If I have this grid structure in any HM, I should be able to meet to 1200. So this is how you will set the limit of the grid check. So for example, if you go to any high power design, then you have to increase the pitch of the stripes. Then for example, if you are doubling it, right? If you are doubling it, then any instance if you take in the middle, then it has to travel only this much distance to catch M2, right? So then you would obviously see 30 to 40 millivolts of benefit when you increase the pitch of the stripes. So then for that particular design, you would set that okay, I should be able to meet 1200 minus 30, meaning around 970, sorry, 1170 itself, right? I should be able to meet to 1170 ohms itself in that particular design. So it depends on the PG structure, first of all, right? And once you have the PG structure, then you'll on your initial designs, you will profile it, you will take 3-4 designs, and you will do this grid check for those 3-4 designs, and you will profile how are my histograms of SPR, and accordingly you will set the resistance limit. So once you set this limit, then going forward, if there is a problem, for example, this via is removed, right? Then for the instance that is sitting here, right, it cannot catch this M2 because there is no via. It has to go to the next M2. Then your length on M1 is increasing. Then there is an additional resistance on M1. Then that is shown in your SPR. The SPR now will increase by 30 to 40 ohms. So you would expect something below 1170, but you might see something like 1220. Then since you have set your limit to 1170, you're going to catch this guy with that resistor. So this is like a simple check that will be able to catch any grid weaknesses in your design, any systematic weakness. It could be a missing via, or it could be chopping of a stripe, a missing stripe, all such issues, right? So it would help to catch.
Okay. Uh, Raj, a couple of questions here.
Mhm.
Yeah. So, like you said, to calculate the SPR, I mean, shortest resistance path, we need a resistance values of those nets, right? Particular nets, PG nets.
Correct.
So, like basically, means from where the information we are reading from the PNR
Okay,
side
so
itself,
okay.
or what are the like means I'm asking in terms of inputs, like is there any inputs required for this calculation?
Yeah, obviously. So we are
And
giving all sort of information to the tool, right? So the information that you're asking, right, that comes from the tech file. Okay.
uh,
So
text
this tech
file,
file,
okay.
is what we would need to give it to the tool. So this will have information of what is the resistivity of each layer for the technology, each
Is
metal
that
layer and via layer.
resistivity? Is that resistivity or resistance we are taking of each
No,
resistor?
resistivity. Resistivity. Then according to the width and the length of the piece, right, in the design. See,
Okay.
it cannot capture resistance of each um,
Net. Net.
each type that you have, right? So
Uh,
it knows the property of that layer, basically what is the resistivity that it can offer with this with unit length and width, what is the resistivity it can offer, then
okay.
what is
So
the
you mean like it is only for a unit length, right? Not for an entire this thing.
correct, it is only for unit length and width. It is
Okay.
for a
I
unit
see.
length and width, what is the resistivity it offers, and accordingly, based on the piece, actual piece that it encounters in the path. Let's say you have this M1, right? M1 is of 10 micron length and maybe zero point 0.3 micron width. So for this geometry, then what would be the resistance of it? That would be calculated by the tool itself.
Okay, okay. And the other question what I had is like you said SPR, right? So it is just a grid check, not the analysis we are doing, right? In the early stages, we are checking only grid check. I mean, what we are understanding is like this same shortest path what we are seeing, right? The same path is used when the actual instance are being placed and actual analysis is taken place, right? By the tool. I mean,
Yeah, that is correct. So, but it
the
doesn't
current
mean
will
that
travel.
only the shortest path is contributing to the current flow of the instance.
Um. Oh, okay. Oh, okay. Okay. Oh, it
See,
can. It
as I have
can.
explained here, right?
Understood.
So, this instance in reality getting current from all these paths.
Okay. Okay. Okay.
Okay,
Understood.
but
Understood.
the shortest path resistance will actually, give the resistance of this. So, see, basically, see, for example, uh, these are all different paths you have. Okay.
Yes.
For
Yes. Understood.
example, if
Understood that.
in
Yeah.
case there is a problem on this path, in reality, when you are going through the PNR cycle, there is a via missing in this path.
Okay.
Okay. How are you going to catch it using grid check?
Yeah.
So let me explain that here, right? So how actually grid check is helping us when there is a weakness going through the PNR cycle, right? How basically this grid check is helping us. So see, when if on this shortest path, in case if there is a you know there is a problem, maybe a via is removed or a stripe got chopped, then obviously then it has to, if it creates a total open, then it has to pick a next uh, next worst path, right? This is not the shortest path now, then it will go to
Okay.
the next next worst path,
Okay.
right, among the all available paths. So assume this is the next worst path. So obviously then you will see that, okay, my resistance of the shortest path to this instance has increased because it picked a next worst path. This is, you are expecting the resistance to come to uh, something like for example 1200, which was given by this path, but maybe this guy has something like 1210 ohms, right? Since this now has become open because of the missing via, now it is picking this instance, is picking this path as shortest path, which is 1210 ohm. So when you see that, okay, my shortest resistance path of this instance is not meeting the limit that you have set initially, then you will
Mhm.
further analyze that, okay, is there any problem around this instance? Then that's how you're going to, focus on this instance and the paths available around this instance. And then you will try to figure out that there is a problem on the shortest path resistance path that originally available for this instance.
Okay.
So
Basically,
that's
we
how
are
you're going to.
making. Yeah. Basically, we are making the grid more robust, right?
Yeah,
Uh.
correct. So you're
So that.
just trying to. It's not more robust. You have created something, and you're trying to make
Mhm.
it intact through your throughout the cycle, throughout the design
Okay.
cycle.
Okay.
You don't
Okay.
want
Got it.
to, lose out any vias, or you don't want to create any chops
Weak,
or lose
weak
any
structure.
stripes, parallel paths that are available. So,
Okay.
for example, if you have some problem on this path, right? So, if you have some problem on this path, then this is not going to caught in the shortest path resistance of this particular instance, but this path will be for sure will be a shortest path resistance for a different instance, right? So in that sense, so then when you analyze the resistance of all the instances in your design, so this instance is going to show higher resistance because of this issue,
Okay.
right? So that's how you're going to catch even this issue as well.
Generally, anything will analyze for the worst analysis, right? So how why we get the advantage of searching for the shortest path, like
Anything
which so if we are doing any analysis
Mhm.
generally, so if you catch worst, then is a possibility of advantage for the further analysis, like doing any static or dynamic. Here we are catching the shortest path for every any instance. So how could it will help for the analysis of a static and dynamic path?
No, so basically, no, here it is not about the worst case analysis. Here, so this is we are just using the the grid check and it's the shortest path resistance to catch the weakness. So see, by this way you are able to catch a weakness that is in the grid, right? When you look at the minimum resistance that you could get to instance, right?
Mhm.
But if something is not offering that minimum resistance, then you would further analyze what is the problem over there. So in that process you're going to catch a weakness that is within the grid. So it is just to catch the weakness. It's not the worst case analysis. Is that clear?
Yeah.
Okay, so can you tell me any example of where we generally find any real
Generally, fine.
case, like a real case like
Yes, see something like this itself, right? So for example, you have this instance, right? This is your M1, M2, as I've just explained. So for example, this is supposed to be your connection, right? This is VDD and VSS, right? So you have a big design like this, right? And for example, I mean, when you started with floor plan, you have this, right? But maybe while fixing PV or something, this VIA got removed. How are you going to catch it? See, one way is, yes, you can finally you are doing airdrop analysis and you know whether this instance is going to violate airdrop. All that is there, but we have limitation in airdrop analysis also. So basically, we will do vectorless analysis uh, majorly, and uh, that is because I mean it has its own. I mean our actual VCD analysis has its own limitations. It may not we may not um, get to run all kinds of VCDs to cover all the scenarios. So that's why we go for a VLS analysis. But even in VLS analysis, also there are problems. You cannot cover whole design. You have to create. You have to go with some switching scenario creation to meet some power, right? So we'll go into the details later, but basically what I'm trying to say is in your IR drop analysis, this you cannot assure that the instance that has weakness in grid may switch or not, right? If in case if it is not switching, then obviously you're not pulling the current that is really needed by this instance. If you're not really pulling, then the drop that you report on this instance is not realistic, right? It's not the worst case drop. then if it is not the worst case drop, then you cannot simply say based on the current drop and say that I don't have any problem with the design. Did you get that?
Yeah.
So that is where our grid check will help. So systematically, whether are there any problems with my grid or not, right? So here, when you have a VR remote, then when you report a SPR of this instance, right, you are going to see higher resistance for this instance because it will travel to the next M2 that is available. It is going to increase the M1 length. So that way you're going to see that okay, there is some problem with this instance. So then you will have to verify in the GUI
So
and
missing
in the
wires.
design itself.
So missing wires will tell like having a least resistance, or
Sorry,
missing wires will tell like it is a least resistance.
missing vias will tell like least
It is a
resistance.
least resistance for that instance.
No, so when you have a via, then you are creating a connection between this M2 and M1, right?
Yeah, so
Otherwise,
that will be least resistance, and if you have proper wire,
correct.
then from the bump to the M1 pin will be least resistance.
Exactly. So if you don't have this via, then it has to choose a different via to catch M2. And
And
the next
so lower layer it will be added, and it will be resistance will be high if there is no
high.
wire.
Exactly. So that's when the grid check will be helpful. So not only this, so even I think there are multiple things that we will check. One is you know so they all check the same thing, basically the PG grid quality, PG grid quality, and what exactly we would verify. One is what exactly we would check. One is how is the resistance of each of the instance, and are all of them are all the instances in the design are connected to the grid or not. So there is something called unconnects. So tool also reports if there are any unconnects. That means any instance that is totally not connecting to the grid. If it is not connecting to the grid, obviously it cannot report a resistance on the instance, right? So among the ones that are connected, it will report a resistance, and based on that, you can see whether if even on the connection whether there is a problem or not. And the second problem is even there can be a totally floating instance also, right? So you will be able to see a list of totally floating instance also. Then you can see, you can review, take the list, and go into the design and see what is the problem, why it is totally floating. And then if there is any short, if there are any shorts, right, shorts in the design, basically you might have a power stripe and a ground stripe at the same region, or power stripe of a domain and power stripe of other domain on the same region. These are expected, right, in general when you are implementing. So you will be able to see the coordinates of the shorts also, and along with that you can even report missing vias in the design, right? So all these are part of your grid check. So all these are going to tell you how whether your grid is robust or not, right? So so
Uh,
this one we have covered. Resistance, basically resist SPR based check to see if there are any outliers more than the limit that you have set. And unconnects is basically if there are any instances that are totally floating, right? So that can happen if your full row, for example, right, you have the standard cell row, you have instances are basically sitting on the standard cell row itself. But what if none of if this total M1 rail, you have M2 stripes also, even for example, but there are no vias at all connecting this M1 to M2, then this total M1 rail is fully floating, right? So that's when you will see even, I mean, this is just an example between M1 and M2, but it can happen in any layer. So that's when you will see even a floating instance then you won't see these instances part of resistance report, but they will be part of unconnects reports. And then there is shorts, as I said, if the pieces of different PG nets or even PG and ground nets are overlapping, then it will create a short, right? And then missing via. So this is another important item. So missing via is basically for if there is there is any overlap of the same net. For example, this is like VDDA, VDDA simply like M1, and this is VDDA M2. There is a overlap, but there is no connection. So tool can report such coordinates and as part of missing vias. So you could have actually a via here that can create a connection between this M2 and this M1. So whenever the stripes of same domain cross each other, and if tool doesn't see a via over there, it will report it as part of missing vias. So these are the important items that actually comes as part of grid check, and that would help us to evaluate the quality of the grid that we are drawing.
Okay, Raj, hello.
Yes, go ahead.
Yeah. So regarding unconnects, right? Like if there are unconnects in the design, so anyway, it will has to check the grid check, right? I mean,
Mhm.
unconnects in the sense like there are missing PG connection to the particular cell, right? To the power
Correct.
pin of the cell. So while doing the IR analysis, will these unconnects will be analyzed, or like they will be dropped from the
They'll be
analysis,
dropped.
IR analysis?
They'll be
Okay.
dropped.
Okay.
So since they are not connecting to grid, then there is no current flow at all, right?
Mm-hmm.
So they'll be
Okay,
dropped from the
then
analysis.
then these are important then, right?
Yeah, this is
And
first thing to
regarding
clean up.
yeah, and regarding shorts, let's say there is a shorts right happening at the beginning stage itself. Okay, PG shorts. So then there will be a overlapping of if we take the in terms of resistive path. So like one resistance VDD resistive path is shorting with VSS. So in that case, how this grid check resistive path will happen, because there will be a shorts,
Okay,
right?
got
Shorting
it.
of
Yeah.
current.
So actually, tool for analysis, it will ignore the short. It will treat as if there are two paths, two different paths for the
Uh,
analysis. It will report as a short, but even when you are even let's say when you're doing dynamic analysis or static analysis also, if there are shorts, then
okay.
tool will treat, for example, if you have, as I said, maybe M13 if you have here, right? And another
Mhm.
M13, something like this is there, right?
Yeah,
And
some other net.
this is VDD and this is VSS. It
Yes.
will report a short, but again, for analysis, it will treat as if there is a VSS and VDD, different VDD and VSS are there available for current travel. And in that way, your analysis will be optimistic overall analysis, because you're analyzing there are two paths, but you can actually accommodate only one path here.
Both in terms of analysis and the grid check, so it will be ignoring, right? The tool will be ignoring.
No, grid check, yeah, even the grid resistance check, yes, it will be ignoring the short,
Yes.
but
Uh,
they will be
but
reported in part of shots.
always should be uh, clean, right? Like this ignorance is happening by the RS tool, but always should be basically clean, right? I
Yeah,
mean,
so this is
shorts clean. DB should be
in general we
shorts clean.
would see in the initial stages of the design. Uh, even I think then, I mean, going forward, obviously it has to be clean
Okay, okay, okay.
for final sign
Understood.
off.
Yeah. Okay, got it. Thanks.
The least resistance check, right? It's the least resistance from the PG, the pin to every instance in the design. Is that correct? Every, even the pillar or the standard cell,
Correct,
right?
correct. From bump
Least,
to from the P lock to every instance pin, VDD pin of the instance and then VSS pin of the instance.
The least resistance power path to
Correct.
each instance. And if that is changing, if it's a little high, then we have a problem. Then there is a problem.
Exactly. Correct.
Or,
there is a problem.
Okay. Even if it's a least resistance check, we are actually looking for higher numbers in that report, right? Higher numbers are the problem, right?
Exactly. So we would, as I said, for that, structure of the grid, we would know that it has to meet to this number. And if it is going beyond that number, that means there is a problem. And we would look at those outliers above that number. We call, for example, outliers or violations. So anything that is beyond that number is a problem that we are not expecting if the structure is intact. So if it is going beyond, meaning the structure is not intact.
Yes, the higher outliers in the least resistance check report is the problem, the bigger numbers,
Is the problem.
right?
Exactly, correct.
Basically, even though it's a least resistance check, high resistances in the least resistance check is the problem.
Right? Is the problem. Exactly, correct.
Okay.
So I would actually imagine is like a, SPR is like a thread. For example, this is your reference. For example, you have this is like your length of the thread, right? So anything that falls in this thread is safer. Anything that goes out of this range, that means there is a problem. So it's like, though we say this is, electrically, it's like a, you're checking through the paths based on the resistance, how far. It's not far, basically. It's in terms of resistance, how let's say how much resistance it is offering from the bump to the instance. So if it is going beyond that resistance, then there is some problem. So see, this is not a final sign off actually, right? So this is, even if it is a little bit beyond the limit, you may not still have a problem in the reality. So that can be, evaluated based on static, dynamic, and all. But at the first level check, you don't want the grid to be disturbed. So when you have a structured grid that you have drawn in the floor plan stage, you're expecting the resistance to be intact. So just to evaluate if the structure has not got disturbed, you are basically using this the SPR parameter of the tool to evaluate it at each of your stage. That's about it. Any other questions? I think yeah, this is it for today. You can ask any questions if you have.
In the chart, like how we calculate PG density, like grid density for any metal.
Okay, so I mean, what density we want? I mean, we would need, right?
Yes, yes.
Yeah. So see, basically, I mean, in practicality, how we generally do is, it's based on some experiments. You would need to see, these are. This is not easy to calculate with hand, right? So actually, what is the current and see, you have lot of parallel paths in the design, and also even the cell current profiles are so complex, right? And this is not in general very easy to calculate by hand, but so what we would do is we would do some experiments with the tool itself. We would basically implement it, and we would see how is the drop profile. It is even both static, dynamic, and how are the average drops, right, with a structure. So these PG experiments I mean, do even the early stages of the design itself, and based on that we take a call. So not only the drop, right? So when you increase the density, you need to check the PD implementation also, whether with that density is my design routable. Are there any congestion issues? Are there any timing issues? So you have to analyze in those two angles. How is my IR drop, and how is the routability of the design, and how is timing closable or not. So these experiment, based on these experiments, we would finally decide uh, with what density we have to go with. So basically some multiple
Generally,
experiments.
yeah. So generally, if you do like a grid analysis, so after my understanding that, suppose let's say like M4 grid has a low density, so having more violations on M1. So how to tell the PD guy or another chip guy telling that you have to increase the density of this much number that we can sort out the issues.
Yeah, so that is easy. So when you do this SPT, I mean, so once in the dynamic analysis, right, you can actually see how much drop that is contributed by each of the layers. Okay, you can do if you see a hotspot, basically you can do report the same thing, shortest path resistance for any instance in the hotspot, and then you will be able to see what is the contribution of each of the layers in the uh, in its path, including the via layer and metal layer. Then you will figure out that there are some layers are the bottlenecks. Majorly, we would see lower layers would be bottleneck. Then, for example, if you're seeing that M4 is contributing to something like 20-30 millivolts, M4 itself is contributing to 20-30 millivolts, and maybe M4 to M3 VI is contributing to 10 millivolts, right? So, and when you totally add the VDD plus VSS drop, you will know that how much you are off from the limit that you have, right? And accordingly, let's say if you have to halve the drop in M4, then obviously you have to go for uh, uh, the half of the existing pitch, right? So
Okay.
that's how you will take the call.
So and the like
How much you are off, and where is the bottleneck, and how much, then based on that, what is the existing drop when you have current pitch, what is the existing drop, and
okay,
if you have to make it half or one third, then accordingly have to increase the pitch, sorry, reduce the pitch.
okay. So thank you. So another question, like in the grid check, we'll do both like short resistance path and equal resistance path, both checks, or only short resistance path will check.
You mean the effective resistance path, effective resistance check? Hello, hello, can you hear me? Hello, can you guys hear me?
Yeah, yes, we can hear you.
Okay, I could not.
I think
Yeah, so maybe
Krishna
if the
got dropped.
question is whether we'll do shortest path resistance check and effective resistance check both in the grid check or not. So the answer is, see, we would, as I said initially, right, effective resistance check is going to take too much time in Redhawk. So there is good improvement in Redhawk SE, Seahawk, the latest version, but the actual Redhawk, for something like 5,000, I mean, some arbitrary number, right? So if for something like 5,000 instances itself, it will take some 12 to 13 hours. And if you have to run on whole design, it may not come in 4 or 5 days. So that's what we have seen. So in general, it is not done. Only shortest path resistance check will be done. But if you have any specific IPs, see, until and unless the grid structure is maintained, so you have this uh, uh, structured grid, right? So that mesh is structured, right? So until that is there, any weakness can be caught by the shortest path resistance. But if any specific instances are connected by a custom grid, then you cannot rely on the shortest path resistance, because if you are going to tap them with a custom grid, then your shortest path resistance is going to change, and you cannot really catch any weakness with shortest path resistance. So in those cases, for those specific instances or specific such IPs, will do generally they will be in limited number. So for them, we will do. We'll go for effective resistance calculation.
Thank you.
Yeah.
Thank
And Raj, like the grid what we have, right? What we import in our PNR run. So who is going to decide that? Like these many
Yeah.
steps
So
should be there in
that
the
that
certain
will
design.
come from IR team itself, the IR sign of
IR
team.
team. Okay, but I heard like there will be some DFP team design for power team. So who, I thought like they will be doing that.
Design for power. Yeah, I mean it may change from so basically the team, they will be whoever is giving, right, they will be
Mhm.
responsible for sign off on also generally. So that
Okay.
team, whatever you call it, so those that team itself will be responsible to give the initial spec, what should be the mesh structure or density for each of the designs in the chip.
Okay. Okay. Understood. And in the beginning, you said RDL, right?
Hmm.
RDL. So is that necessary? Like, can't we like how exactly difference between this normal layers and that?
No, there is
Like
maybe so there is no difference as such. Basically, it is just the topmost layer on the die.
okay, like we can use the topmost layer from our design itself. Let's say M11 is the topmost layer of our design, so we can directly connect to. I mean, can't we connect directly to that to bump? Do we
Yeah,
really need the
we can.
ideal part?
No, no. See, we can connect. No, there is no problem. We can connect, but in general, see, it is already in general. What we see is it would be a hierarchical implementation. So some layers, the topmost layer in general, will be part of SOC SOC def. Okay, SOC
Mm,
design, and
mm.
then the sub HMs will have lower layers implemented. So then that will be finally integrated. So when so because you might have very small uh, macros, right? And in each macro, there can be very smaller macro that you may not even get a single bump on top of that. You might have to take the connectivity from adjacent head macros. So in such cases,
Okay, okay,
adjacent
got it,
blocks.
got it.
Yeah, so in such cases, it would be difficult. So that's why it is owned by the SOC team, final
Okay, okay.
integration team. And at a block level, you will have only the lower portion of the grid.
Yeah, yeah, understood. Yeah, understood. Uh, Okay, for if my understanding is correct, for ideal is like it will be designed for entire a full chip,
Exactly.
right? And from there, it is distributed in the respective design
It would be
through
distributed
the
like
design.
each of the blocks. Correct.
Okay, 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 got it.
Okay, then yeah, maybe we can continue the discussion in the next session if you have any more questions. Okay.
Yeah, when is the next session? Tomorrow we have at what time?
Yeah, I'll convey to Srinivas, based on my schedule. Okay, then
Sure, sure,
you might get informed.
One
sure. Yeah.
Okay.
feedback. Hello.
Yeah, yeah, yes, go ahead.
One feedback. some little snippets or diagrams on the report, right? Whatever the least check reports, some pictures, little screenshots on the grids and all. Actually, would help a little in understanding, I think.
Yeah,
Just a,
exactly. Yeah, exactly. I would agree with that. Yes,
if you get
that is true. I think even I think when we set up the Redhawk session, right? Even I think we should be able to go through the reports, the tool report, what where are actually the reports and how is the structure, and even let's say when we talk about SPT, how it actually looks, right? What all we can see. Yeah, all that would actually help. But yeah, unfortunately, I don't have it right now. But yeah, I'll try to get that for our next sessions. Thank you. Yeah, thank you guys. Thanks for all your time.
Yeah, thanks Raja, it was informative.
Thank you. Thank you.
Thank you.